You see the,
yes.
yeah? Okay.
Looks good on this end.
All right. Hello, everyone. Sorry for the little delay. I thought it was in the other room. Everything was supposed to be there, I thought. Anyway, so, yeah, so welcome to my talk on generating architecture-agnostic performance tests from functional unit tests. So I will present this talk, but the hard work was done by Daniel Sergio Vega Rodriguez. So he was a master student at USI, Università della Svizzera Italiana, and I supervised his thesis together with Professor Olaf Schenk and Timostonis Pasadakis. And yeah, so that is really the development of the package I will show is really his work. I have been contributing by it was my idea to do that package and to think how to do that, etc. But he did the hard work. So I will talk about motivation, fundamentals, package design, how to use this package called perftest.jl, the results and conclusions. So first, motivation. There are HPC examples that show that it would be really good to have a unit testing, unit performance testing framework. So to test performance at unit level, just like we do it for functional tests. And so actually the very beginning was exactly this implicit global grid that I've been developing at CACS. And so this package does a halo exchange, like it says here. And to do that, there are like different layers of abstraction. And in order to copy the halo with very low-level functions, and then on top of that, we have more abstractions and so on. And so in order to make sure that at every level of abstraction we don't lose any performance, I thought, well, I should test that. And I want to be sure every time when I have a new version that I don't lose any performance, right? And to test that every time is difficult. And I don't want to go to dig in every time to see where now I lost performance. And so I actually started to do like an ad hoc performance test. I copied the whole performance, the whole unit test suite, or less not the whole, but a part of it, and transformed them into performance tests. Then afterwards, the problem was that to maintain this was a lot of work, right? And so that's why I thought actually that would be a good student project to do that. And then there is a second real-world problem that we looked at, that is Paradiso.jl. And so, sorry, just one. It's a bit far away, so difficult. Okay. So there is a second use case that we looked at, the Paradiso.jl. So it says sparse linear solvers that are which are key components in many numerical computing algorithms. And so input matrices can have very different sparsity structures given the field of origin. Now imagine a user who installs Paradiso as a dependency for the project, then the user wants to check that the package is performing as expected before using it. And so with a framework that you can just run that checks that the performance is fine, not only the functional tests succeed, that's really good. And we see afterwards, in the end, how we really could test that and the difference it made. Yeah, so in summary, the motivation is to facilitate the development of unit performance tests for HPC applications. And in addition, we want to do that in an architecture-agnostic fashion, such that these tests can run on different machines, that you don't have to do new tests for each machine. And so we do a Julia package to implement this concept, this idea. So the fundamentals of this idea. Well, first, performance testing, you're surely aware about that. We have different metrics, right? Time, flops, bandwidth, iterations per second. And while in functional testing, it's obvious. You have an expectation for a result, and you check against that. In performance test is not so obvious, and so we deal a bit with that. And besides that, so this is not only new in the Julia world, this is really something new in general. If you search in literature, you don't find anything like that. Now, we want to do architecture-agnostic performance testing, as I say, and so it means that we will normalize the values from the metric, for example, flops or bandwidth, throughput, memory throughput, or effective memory throughput. We will normalize that. Check it against a reference to see, for example, okay, we got 80% of the expected performance. And so we want to do declarative performance testing. So we want to say, we don't want to say in detail how to do it every time, but just to say what we want to test and what methodology to use. And you will see later what methodology means exactly. And so here you can see an example of how it looks, this code, right? So you see we have a test set, just like in functional tests. Then we create some data, we initialize some data. Then we do some computation here, the inner product. And you see we put this perf test macro in front of it to make sure that now this computation will be checked for performance. And just the 2 lines above showed what we will be checking against. So we will check the maximum time against a certain value that you define here, function of the number n, and the median time. And so we check that these two conditions will be checked every time. Now, the performance testing methodologies that I mentioned. So we have either a simple regression testing, just to check, did it go down, the performance, compared to the last time we ran it? But we also have testing with effective memory throughput or roofline modeling. So we can check that the effective memory throughput, which is basically when you consider only what has to absolutely minimally travel from your main memory or global memory to the processor and back, and you don't consider any redundant reads or unnecessary reads or writes. So that's the effective memory throughput. And the roofline model, surely everybody's familiar with. You see in the bottom right how that looks like, right? You have this roof. there is a corner, and so the first, when it goes up the roof, it's memory bound, and afterwards it's flop bound. I mean, compute bound. And so, and yeah, I mean, on the y-axis you have the flops, and on the x-axis the operational intensity. And so now this package can then draw that based on what you obtain, based on the results. And you will see this in the results. So the design of this package so why Julia? Well, I guess here I don't need to convince anybody why, but let's just say metaprogramming, of course, is very powerful for this. The ecosystem that we have, also including that we have already this test suite for functional tests. We have benchmark tools, etc., etc. And we have a growing HPC and scientific community. Now, here's a little outline of how that works. And so you can see that there is there in violet you see test set, right? And inside, in blue, we have local initialization. So in each little test set, you have some initialization. You initialize some arrays or whatever. Afterwards, you have computation. And then some functional tests. And local finalization. And so what's the key here? The key is that in functional tests and in performance tests, we have the same essential structure. We initialize something, we compute something, and we check if either our performance or our results correspond to expected values. And so we make use of that in this package in order to have both in one single file. Let me check. Yeah. Then, so then it goes through this transformer, through this package that uses macro tools in order to transform this initial code with unit tests and performance tests to transform this in some actual code that can then do this testing automatically using benchmark tools, etc. So it uses this benchmark groups feature from benchmark tools. It uses advanced features from benchmark tools. And you see, so when you generate the functional test here, when you generate the performance test, the functional tests are going to be removed, right? So such that you can run the functional tests independently from the performance test and vice versa. This package implements a new type of test set that holds extra features meant for performance testing. And the test sets of the recipe file are transformed into this new implementation. Now, how to use it? So here's really the essence how that works. You have some Julia project, you have some unit tests, and So you add this perf test macro in front of what you want to test, right here. Before that, you do a certain configuration if you want, and afterwards you have the unit tests. And it goes then either you generate the performance test or the unit tests, and you're done. Now, how to show that, to point it out a little bit better, you can see here really well that the result from the functional test is the same as what you computed here in the performance test computation. Now, there is a lot of possibility to customize. So you can define new metrics, and you can use some special symbols here, like this here, median time, in order to define very quickly your metric that you want to use. If you want to not to use effective memory throughput or roofline. Then, of course, you have some documentation. And now let's look at the results. So first for the implicit global grid case. So here we measured the effective memory throughput. And the unit, the particular unit that we chose here to show for the example that was tested was the transfer from the received halo to the local domain array. So this means the following. So what is obtained there in the blue, in the halo, and then what is obtained there is obtained in a buffer first, and it has to be moved there. This buffer can also be on the host, right? Doesn't matter. But so we have CPU tests, GPU tests. So meaning that in the GPU case, it's when you have a problem that you solve on the GPU. And so it will test the performance against the expected values, which are obtained with some benchmark, in this case, the stream benchmark for CPU, or something similar for GPU. Or actually, sorry, for GPU, it's actually the bandwidth between the GPU and the host, right? So whichever connection that was, PCI Express or something like that. And so we get there the theoretical value, and next to it, you see, measured is what we obtained with the package, and you see we got almost 100% everywhere, so it's good, right? But if at some point it would be lower, then it will flag that. Okay, you got down to 80%, you need to do something. And so actually here we had 91% in one case there. So there actually we need to go check what's happening, if that's not improvable or if that could be better. Then for the linear solver, paradiso.jl. So this example features a unit test on the factorization step, and that's the most computationally demanding. And so we include here two input sources, diffusion matrices and real-world matrices. So these real-world matrices were really extracted from real-world data somewhere to have something very meaningful. It's from civil engineering or material science. And now here's something really interesting that brings us, that shows another interest besides the development of the code, besides that it helps during development. It shows that when you use, for example, this Paradiso library, you can, when you want to just use it and run it, that you can first check after installation that your installation was done in a good way, right? And so, because here we tested with two different BLAS versions, and with one we'll get much better results than with the other. And so when you have, so this performance test would then also show you, oh, you did something not well in your installation, right? And so here you see the results. You can see always on top here, the points are the results with Intel BLAS, and on the bottom are the results with the other one. And the Intel is outperforming very much by like, factor 3 or 4 or so, depending on where you are, where you look at. And then so the next thing is that as a developer, you decide where you want to set the threshold, right? Where you want to say it will flag a regression or just that it's not fine. And so this threshold is this blue line here. And actually you can also do this threshold that it really follows the roof line. That it's not just one value, but that it follows the roof line, that you say you want to have 80% of the roof line or so. Then as a little bonus, we have the Bencher platform that we use, and we'll show you how that looks like. So this is a CI/CD performance regression platform. And so there, usually they just check if before the last time the performance was worse, right? Or let's say the runtime was worse, and that's it. But we can also put all our data in there. And so you can then compare between Git branches and commits, between machines, between software units, between metrics. And it supports also other languages like C, Rust, or Python. And so perf-test.jl offers a Julia adapter in order to put that there. And now here on the right you see the example. You see here 3 lines, 3 different colors. And here in the vertical you have the different versions of a certain branch. And so we compare here between different versions. And you see the blue and the red line, they're flat. So it means we have no change. So that's usually good, right? Because what we measure here is the median time. But this one here goes up very much. So we see, okay, with our last changes that we did, we have now, our solver takes much more time or whatever it is. So with that, I get to the conclusions. So the performance regression unit testing is a largely unexplored practice, and I believe it really holds very significant potential. I believe it can really improve how we can develop our codes, and we can save time in the end. It helps both to maintain it, but also the development itself, that you are faster when you always see how things work out with respect to performance. And as I showed also, besides development also, it allows you to quickly check if an installation was done correctly, if you have the right dependencies used, etc. Voila, and the effectiveness of the package was demonstrated in 2 real-world examples. And we have a little paper here submitted called Generating Architecture-Agnostic Performance Tests from Functional Unit Tests. Future work is to integrate performance counter use, for example, liquid, mature the bencher work there that I showed before, and to increase extensibility and configurability. But yeah, so this is really an ongoing project. The student that I told you is now doing a PhD, continuing this work. And so yeah, this is really something being worked on very hard daily. All right, with that I conclude. Thank you very much.
One thing that I noticed, I was wondering about a little bit, was there's, in the perf compare macro, there's typically a constant. How does one choose that constant? Like, you know, do you do it empirically? And if I took, you know, some of this code and ran it on a Raspberry Pi, for instance, would the test pass there, or would it depend upon the hardware architecture? Like, how do you reconcile those things? You
mean how to define the threshold?
So like there's like a perf compare where like you compare the, I can't remember if it's the median or the mean to like a function like 0.00005 times n. How do you where does that number come from?
Can you example that?
Yeah, well, that's maybe a bit a contrived example. You should rather think about you choose a metric like memory throughput, right? And you say, if I am at 90% of the peak performance that I can get on whichever machine, I will say I'm satisfied. I don't want it to flag, right? If it's below, it will flag. You just say it's not good. And so you choose yourself, like what's the percentage of the peak performance of whatever metric, and that's it. Was that clear?
So is that dependent upon your machine, that peak performance thing? It like takes some like scaling based on the machine? Is that what that means?
Okay. Let me show the other slide again. So here, for example, where it says benchmark. So this is benchmarked using the stream benchmark, right, on the top. And below it is with a tool from NVIDIA to check what is the best speed you can have between CPU and GPU to move data. So these are benchmarks that you can find or just create yourself. And then this will give you the peak performance. And then afterwards, you set the threshold that you say, I need to achieve with respect to this peak performance.
Makes sense. All right, thank you.
Do you keep do you have like an archive of these machine-specific benchmarks, or does the user provide them in like a preference or something like that?
Well, so far there is effective. Well, this is the stream benchmark. There is this other benchmark that I just mentioned before. And that's for flops. For flops, it uses BLAS, matrix multiplication. I think that's it for the moment. But you could also choose yourself a benchmark. But I guess one can extend that. Yeah.
What I mean is like, does the package have like a list? Like if I'm on an A100, I already know the numbers for that processor, or does the user just stream themselves and put the numbers in like some global setting somewhere?
Yeah, you can also put the numbers if you know them. Yeah.
Okay, right.
But let's say the advantage of running a benchmark is that you don't need to do anything, right? You don't need to have exactly a list for A100, for V100, for H100, et cetera, et cetera.
So when I was listening to this, I originally understood this as that this process you have, it will automatically, by default, it'll automatically run these benchmark programs for your machine. Did I understand that correctly, or?
That it will automatically run the benchmarks? Yes.
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 Yeah, okay, yeah. That's what I thought you were saying at first, but then I think some people were hearing the alternative interpretation was that you had to implement you had to run them yourself and plug them in. And so I was like trying to figure out which one it was.
Yeah, so there are a couple of benchmarks, like I said, for flops, for memory throughput, for data movement between CPU and GPU. But if you need something else, then you either need to plug in the values directly if you know them, or create your own benchmark.
Yeah, thanks.
One follow-up. Have you looked at MPI yet?
You can also use that with MPI, yeah. You just need to make sure that after the computation you have a synchronization. You need to add a barrier.
What I was thinking more like is we could just take the MPI.jl's test suite and then run them nightly, and then whenever the system software gets updated, we can get a, I'm thinking like reframe basically, but better. I don't know if you thought about that.
To include it in MPI, you mean?
No, what I mean is make it part of the system checkout after an upgrade.
Yeah.
So
in MPI.jl.
Yeah, so we could just take all the MPI.jl tests. So what we currently do is we use reframe and the OSU MPI benchmarks. But then there's a lot of, I guess it's a little bit slower, but probably okay. And I'm thinking this might be a much nicer way of systematizing that.
Ah, yes.
I wanted to get your thoughts on that.
Yeah. So basically, when as a supercomputing center, before you return the machine to the users, you want to check, is the machine running fine, right? And so you said you use reframe until now, where you have to create little checks all the time, and you check only, what you really by hand with hard work implemented. But this way you could really just, if this is systematically put into MPI.jl, you could just run that as well in order to check if the system is healthy, right? Yeah, absolutely.